Yes, I'm going to talk a little bit about AI, and I'm going to talk a little bit about a future perspective. What do we need to solve in the next few years? What do we need to work on? And what specifically are our interests here at RISE SICS? What do we want to work on, and what do we want to build? And I'm going to start at the very, very basic, just to make sure everybody is on the same page, basically. So what is machine learning? So machine learning is the ability to learn and predict from data without explicit programs. So instead of just manually crafting programs, or for example, expert systems or something like that, you're representing human knowledge, you build a model that you can train by looking at just lots and lots of examples, and you train it to do something. So this has become a key real cornerstone of AI. This is a part that really starts working now. And we really, really need this to build real AI systems. So machine learning has almost become synonymous with AI in the last few years. However, this is not at all true, and we'll get to this in a short while, basically. So why do we have all this hype about machine learning at the moment? Well, we've had a few really, really successful examples, mostly within the area called deep neural networks, which is take a neural network, which is a simple model approximation of the human brain. Just take an input, weigh it by linear weights, put it through a nonlinear transformation, and put it to an output layer. So if you stack lots and lots of those, and you're able to train them, you can actually represent abstract concepts in, for example, images. So at the first few levels, you represent more lines and things like that, later on patterns, and perhaps at the top, human faces and things like that. And this is an incredibly powerful tool. So this is the performance on a standard object detection database. So in 2010, you see that the performance of the state-of-the-art was so-and-so. The performance in 2015 and 2016 is really, really good. So this is the error on this database. It's the error. And the red line represents human performance. So for 2 years now, machines are better at this than people. You can also train these things to do a lot of other stuff. These are actually just training examples. But for example, if you have both text and images, you can train these things to look at an image and generate a description. I'm presenting this picture because I'm going to actually use it later on to say that this doesn't actually really work that well. But we really have to look at why do these things actually really work well now? Well, first of all, of course, there's increased interest, more investment and things like that. Of course, we're better at methods and algorithms. But if we're looking at, for example, deep neural networks and other techniques, what really changed is that we have a lot more data and we have a lot more compute power, and we know how to harness it. This was the key point that made these things work. By using these things, we can build huge representations of the world and actually train them. And right now, actually, within the area of machine learning, one really, really big issue is to understand why these things actually work very well. Because if you just look at it mathematically, they should not be as good as generalizing as they actually are. So this is really, really interesting. But if we really, really want to build AI from these systems, you need a lot more things from these models, basically. And this is what we're looking at SICS at the moment. First of all, we need to make decisions based on the output of these models. To actually do that, we need results in time and based on fresh information. We need to train and predict basically in real time, in really, really short time. Nowadays, all these models are really batch-oriented. You take a lot of data, you train it for a long time, and you deploy it, and that might take some time. We really need to fix that. We really need to build causal models. We need to understand what causes what, and not just how things are correlated. Perhaps even more importantly, as a first step, we need these models to be able to tell us how unsure they are about a prediction. So if you, for example, predict that there is something in an image when you have an autonomous car or something like that, it really, really makes a difference if you predict that it's a, I don't know, garbage bin or something like that, and you're really certain, or if you predict that it's a garbage bin and you're really uncertain. The decisions are going to be completely different, basically, because in the latter case, it might be a kid or something like that. And if we really want to base real decisions as a human or an AI on these models, they need to be able to explain themselves. Why do they make this prediction? This is very lacking today. And the other thing that we're trying to solve at SICS, that we have unique competence in solving, is the fact that ML really, really lacks in efficiency in several dimensions, basically. First, in terms of data. We really need a lot of data to build these really good, complex models. We need to fix that. But they're really also inefficient in terms of computation. We really waste a lot of power here. And here we're going to build systems that fix that. And they're really inefficient in development time. You would be surprised how long it takes to build these really, really advanced machine learning systems that you see as examples, fantastic examples of successes, basically. So we really need to fix that. So let's get back to artificial intelligence. And artificial intelligence is way more than just machine learning. It's not just learning how the world works from data, it's actually making active decisions. And machine learning has been around, artificial intelligence has been around for a really long time. It was defined in 1955 as a proposal to a summer school by some people that you might recognize, John McCarthy, for example, Marvin Minsky, and some Claude Shannon that did some contribution to science. But he was actually part of naming this. So it's been around for a really, really long time. We have a massive amount of results, basically. And if you look at some things that have been presented as real amazing progress in AI for the last few years, we can take, for example, the AlphaGo example that Google presented last year. So last year, Google built a machine that actually can beat world champions in Go, a very, very complex game. In this, they do use these deep neural networks to try to basically guide the thing through the search space. So what you do is that you look at the position on the board, you try to play out all possible games, basically, but these are a lot of games. They train these neural networks to guide the search so that we don't have to search everything. But another key component that is probably even more important is that they built a really fast Monte Carlo tree search algorithm. And this is from a completely different part of AI, basically. But this is what this AlphaGo work, basically. So there's a lot of other stuff from AI that we're now bringing in to actually build these systems. Now, let's go back to what we actually really need to build to make more smarter systems. So let's just think about a very, very popular sciencey concept, basically, that Daniel Kahneman defined in a book called Thinking Fast and Slow a few years ago. There he talks about two systems, and these are actually not too bad metaphors about what happens in the systems that we want to build as well. So system one is basically really fast and intuitive. It's just reaction, basically. System two is much slower, but reasoning, thinking about the results and things like that. Right now, in machine learning, we're building system one. We need to build system two. This is incredibly important. To build the next step, we need to build system two. Because if you want to predict, for example, what's in these images based on just training data, and you this is presented to a deep neural network that was trained on standard data. If you look at the middle picture, an airplane is parked at the tarmac at an airport. I mean, this is not, you can see why it describes it like that. There is tarmac or something similar, there is an airplane and so on. This is the logical conclusion if you just react, basically. But there's absolutely no reasoning behind it. So this is what we at SICS really want to do as next step. I'm not going to go into detail in this picture, because this is just a really brief overview of the AI systems that we want to build. But basically, what we are good at the moment is the perception part. We can actually perceive the world and make quick decisions. in the next box there, the reasoning part, we're really not very good. And at 6, we're actually looking at bringing in other parts of AI to machine learning to build these kinds of systems. So this is a graph representing, I think it's actually Wikipedia, but Olof Jörnerup, who created this picture, might actually have another opinion. I'm not actually sure. Okay, good. It's all words existing in Wikipedia. And you look at every word and how it correlates, how it co-occurs with other words, basically. And just from that simple statistic, and if you look at these distributions, you can find out how exchangeable words are, how similar are they in use. And you can cluster them, find abstract concepts such as colors or vehicles and things like that, and actually we can start reasoning about them. And we can start reasoning about these things perhaps in terms of analogy and things like that. So if you want to, just from a massive amount of text, find out who Barack Obama's wife is, you put out a question. So Barack Obama relates to X as husband to wife. What comes out, basically? And we're starting to be able to build these systems. Another core concept that we need to fix, though, is the fact that if you just look at text, this is an eatable tropical fruit. Nobody states the obvious in text. Nobody says that it's yellow. This is too obvious to actually write about, basically. So what do we need to do? And this is actually a core concept to actually build real AI. Well, we need to look at multimodal data. So if you look at text together with images and things like that, you can actually see these concepts as well. You can see these obvious statements. This is an experiment done on, now you can't see that, that's actually, we have been using a deep neural network to build abstract concepts of what's in images, basically, and do a classification, and then using standard techniques for natural language processing to build these graphs that we can actually reason about, and it can detect concepts here. And we can do this in the future, hopefully, on a really fast and large-scale manner on all kinds of multimodal data. So one of the key things that we actually need to do to bring these systems to life is we need to build a home for them. We need to build a real home for machine learning and AI. There is no such thing yet. We spend enormous engineering effort to build these really, really large-scale systems. We need to fix that. But we have a plan. And Saif Haride here is the PI for the project that is going to be the core of AI research and machine learning research at SICS. And here we're actually going to build all platforms, all the way down to implementations, systems, and so on. So if you look at this, the last 5 years or so, we've been working on cloud computing, stream analytics, and so on. Now we're moving to continuous deep declarative analytics. So what do we mean by that? Well, by continuous, we mean non-interruptive, non-intrusive processing, and models that learn and train continuously, basically, continuously updated. By deep, we mean complex properties in the data can be modeled. They're interpretable, layered, like, for example, deep neural networks, and so on. And computation-wise, arbitrarily iterative, and we can combine both historical and live data. And finally, to fix this problem of productivity, they're declarative. Convenient programming models for any type of data. If we're working with a graph representation, if we're working with tensor representations, or anything, we're going to provide a system that is completely transparent. And this is basically what we envision now at the moment. At the top, we're going to do a lot of work on theoretical ML, addressing the questions that I've just described for you. And under that, from the bottom, we're going to build a distributed runtime that performs optimizations in runtime and can provide live progress monitoring, an intermediate language on top, and at the top, declarative programming. That means that we can have a complete system to build AI solutions on. And now just to conclude, because my 15 minutes are over, just want to summarize a little bit what I've just said. First of all, AI is a lot more than just machine learning. And I'm saying that as a machine learning researcher. I would also like to say that there is a lot more to discover and rediscover within AI that we can actually put to use, as long as we have large-scale systems to work on them. Reasoning systems are key to learn from small data and to actually build really sophisticated solutions. We really need to broaden our scope of data to build wider AI, and systems and platforms matter enormously. We're not going to be able to build these things unless we take a whole view of the whole complete system stack, basically. But that's what we're going to build in the next 5 years. All right, that's it for me. Thank you very much.
Thank you, Daniel. Do we have a question from the audience? It should be a lot of questions. I think there are really... No? Over there.
Daniel, I'm curious to ask you, how would you think to build System 2 thinking machines only by processing text and images? So what is the role of symbol grounding, of situated learning? So the role of the body to come to this System 2 thinking, which may include cognitive functions like reasoning, attention, and things like that.
Yeah.
Thank you.
Yeah, very, very good question. And no, I don't think, as a very general answer, I think that if we want to build something that really represents an intelligence that sort of reflects the intelligence we have as humans, we need to also build something that manifests itself sort of as a human. So it's not just text and images and so on. It has to be some kind of agent that sort of lives in a similar world that we do, basically. So there's going to be a lot more work to do, a lot more types of data and things like that to build that kind of general intelligence.
Mm-hmm. Thank you. Yeah, it's really interesting because there are always these questions about what kind of reasoning are you seeing forward?
In these models?
Yeah.
Well, hopefully more and more general questions so that you can actually do basically unsupervised learning and ask it more or less any question. Ask it to predict whatever or ask it about the probability of any kind of relation between symbolic concepts in the data, basically. Hopefully. Yeah. But this is going to take time.
Yeah. Good. We have another question. Yeah.
Okay. It would be interesting to know what kind of application areas you're using when you're starting this. Must be some. Is it text, quantitative, or a combination, or images? So, or which kind of customers do you have in the beginning working together with you?
Right. So we have our close partners. For example, Ericsson within telecom, Spotify within, Volvo have lots of applications both in, for example, vision and in all other areas, so within transportation. But then again, to try to develop these things, we also need very, very large data sets and so on, and we use what is available, basically. So good starting points are text. There's a lot of text. There's quite a lot of images as well and so on. So all these things are very, very good and straightforward starting points. So it's a bit of both sensor data from all of these systems that we're talking about, but also more public data to bootstrap ourselves.
Great, thank you. Sorry, now we don't have any time left. But Daniel,
yes.
What are your impact on sustainability? What are you doing on daily basis most? Is it economical, environmental, or social, or?
Oh, this is everywhere. This is can I put a ball in everything?
Yeah, of course.
Yeah. Okay.
Good. Thank you very much.
Thank you.